mute. Yes.
Okay.
So,
No, now I just have to find my pointer here. Okay. Yeah, that works. Okay, good. All right, yeah, then let me just dive in. So the whole project model started with a seemingly simple question, and it is, what is it that actually generates the axial and eta prime mass in QCD? And the thing is, the average phenomenologist, and also myself, maybe half a year ago, would have said, of course, it's instantons. With instantons, explicitly break the Cornell symmetry to the anomaly, and therefore they should give a mass to the axion and also eta prime. But you think a bit more closely about it, then there are a few doubts that instantons would actually generate a potential for that they give the leading contribution to it. I'll come back to that a bit later. But it's very tempting to just write down a Fluke operator, close up all the zero modes, and stretch off the potential of eta prime or the axion. But once you start doing that, you already see the first problems arising, because the largest contribution would come from the region where QCD is strongly coupled. But this is also the region where the instant calculation breaks down. You could also say, yeah, we could just try to extrapolate into that region. Let's just introduce.
Excuse me, may I interrupt you from the beginning?
Okay.
I think you might skip it because everybody knew from 1974 that instanton is not suitable for the mass calculation. It's only an example of a field configuration which provides what it needs to provide. But for the reason which you explained, it was, I mean, I don't know why you say that everybody knows. Everybody knows that it's not instanton. Instanton is not defined at large distances.
Yeah,
and this is extreme infrared effect.
Yeah, I completely agree with you. What I'm more getting at is that in the phenomenological community, many people did not know. And yeah, exactly. And this is the question you also read in many reviews. Instantons generate the Axion Mass and eta prime potential. And our goal was also to propagate this knowledge to the phenomenological community and give reasons why it would not do that, and also give for a different direction. But I'll get back to that. Okay, yeah, like you said, for large instantons where the gauge theory is strongly coupled, the whole instant calculation breaks down. You would in principle need an IR cutoff, but what would be the IR cutoff? The whole calculation would be sensitive to this IR cutoff, extremely sensitive. Also, you don't know what role does confinement dynamics play. And there, also for these reasons, it's very doubtful that instantons would give a main contribution to eta prime potential. And if you didn't know about that already, what might make you doubt that instantons give a contribution to the eta prime potential? One reason to approach the whole problem is from a deformation of QCD. You look at large N QCD with a fixed tooth coupling. Instantons seem to be exponentially suppressed. So the instanton sector depends on the N, so the number of colors. And if you take the number of colors large, then instantons seem to be exponentially suppressed, and you would not expect to get a contribution to the eta prime potential. But at the same time, already Witten recognized that the vacuum energy still has a non-trivial dependence on the theta parameter. And this non-trivial dependence, he said, would be a function of theta over n. And already here you see that it cannot be an instant effect, because an instanton would not give you a theta over n dependence. It would give you something that's trivial to pi periodic in theta. So here in this case, in large N, it would be confinement dynamics, fluid condensation, and so on, which would generate potential for the eta prime. Now the question is, what happens in finite N, the finite number of colors and finite number of flavors which we have in QCD? And in order to see that, it would be nice to actually,
can we go back to the
Yes.
When we can conjecture this form of the vacuum energy, the data depends. I guess, and that comes from the fact that when you take n goes to infinite, the eta prime should be massless. But is there another way to see that data dependence of vacuum energy of the asymptotically frequent schemes?
So as far as I know, this was a conjecture by Witten, and it was motivated by theories in 2 dimensions. They could actually find the dependent vacuum energy where you got exactly this dependence. So in principle, you don't know, you can't solve QCD exactly, but this is a well-motivated guess from theories that we can solve.
I think there are low energy theorems which are pretty strict derivation, and they it's not a conjecture, that's a fact.
Okay. Good. All right. Then, so in principle, you would like to see this explicitly, not only from a large N limit, and check it explicitly in QCD, but unfortunately, QCD is strongly coupled, so we cannot do that. Can really check what is going on. So we tried to do the next best thing, to check in a theory which is QCD-like, which is as close to QCD as we can get. And in our case, we looked at softly broken supersymmetric QCD, broken through anomaly mediation. And in this case, in supersymmetric QCD, you have the added benefit that the non-perturbative effects are actually known. You can fix your superpotential and you know the non-perturbative effects. And also, what also helps is that supersymmetric QCD, with anomaly mediated supersymmetry breaking, has vacua which are QCD-like. This was shown in a serious paper by Hitoshi and Chaba in the last couple of years, where they showed that when the number of flavors is smaller than 3 times the number of colors, so whenever supersymmetric QCD is not IR3, then you have chiral symmetry breaking vacua, which are QCD-like. And in principle, if you would be able to take the Zubi breaking above the strong coupling scale, then you would also recover regular ordinary QCD. But this is, of course, your calculations break down, and it's not even clear if there's a continuous limit. There might be a phase transition when you take the Zubi breaking above the strong coupling scale. But we hope that this can give valuable lessons for ordinary QCD just by looking at the supersymmetric theory.
But what kind of lessons what kind of lessons are you thinking about here? Because it's not instant what you're trying to give an explanation in QCD, but as Misha said, it's understood. That's why. Is that what you're going to do?
Yeah, so our hope is by computing something in a strongly coupled theory that you can actually solve or compute to some extent, that we might learn something about how QCD actually works. Of course, you don't really know if in the end, if you can do this continuation from taking the Zubi breaking scale above the strong coupling scale. It's not clear if there will be phase transitions or not.
Yeah, it's not continuously connected.
Well, in principle, we don't know it. It might be, but it might not be. There might be a phase transition, there might not be. It's not clear. Yeah.
Excuse me, may I interrupt you for the last time?
Of course.
I want just to make a note with regards to the introduction. I don't know what's going to happen with supersymmetry, probably very interesting, but okay, in just regular QCD with light quarks, you can use chiral analysis based on all sorts of low energy theorem which exists for soft methods. And you can make 2 statements or predictions if you wish. The first is of a qualitative nature. If for some reason, we don't know what, for some reason, if the prime doesn't have a mass, or better to say it has a Weinberg mass, which he calculated in current perturbation theory before instantons were known, then there is no theta dependence whatsoever, even if it is present at the Lagrangian level. All quarks are massive, so it seems that they might be theta dependence, but all the contributions, if you use at least in the current perturbation theory of piles, eta mesons, and beta prime, they combine to cancel each other. Second, you can just calculate in terms of the chiral theory parameters, you can calculate the mass of the axion or using chiral perturbation theory. The mass of the axion is coupled to GG dual, So, and you can find exact correlator of two GG duals at zero momentum through low energy field. So you know the mass in terms of F pi and pion masses and all that stuff without eta prime, because if this limit, if you assume eta prime is not light, then you don't take it into account. If you take it, it will vanish. So that's a little bit more was known, in fact, from late 70s about how to get the Axion mass, how to relate it to the eta prime mass. I mean, it's not just, somebody came and said that it is from instanton, we cannot calculate instanton,
No, but
that's the end of the story.
But that is used in the phenomenological community, the connection of the axial mass to the pion.
Yes,
Yeah,
this is a
that's used.
well-known
It's
formula.
well known.
It's pi. What you need to know with pi and the pion mass, eta prime mass. If you want to improve the accuracy, you take into account the mixing between, say, pi
Exactly.
naught and eta naught.
Yeah, exactly. Yeah. But that has been computed in the phenomenological community, and it's been updated.
Well, it was computed, I think.
No, I know the original. It's updated. It was just
Yeah.
updated.
Of course,
That's
all these mixing angles were
Exactly,
taken
yeah.
into account
Yeah,
and
yeah.
all the experimental improvements. So it's a story which came to now in 2023 from 1970s, maybe late 70s, but still, it is at least 45 years old.
Yeah. Okay.
So you didn't pay credit to
You should have added.
all these people.
You should have been making another slide. You didn't have a slide.
Yeah.
Production.
Yeah, exactly. Yeah.
Things would have been different if eta prime mass were close to Weinberg boundary, right? Not exactly, right? Imagine that you
No, eta prime mass is much larger.
I know. That's why we recognize the problem early on.
Of course.
If it would be close, right, but not exactly.
Yeah,
Then
that's
it would be a difficult situation.
difficult, yes, but fortunately, it's not close.
But this was also understood in the early 70s in the old language as a statement that the Zweig rule doesn't operate in the single scalar channel. That there is a lot of mixing between this SS bar and the UU bar, DD bar masses. And that's not true in the vector channel, which is why the omega and the rho are ideally mixed and the eta and the eta prime are not ideally mixed. So the real question is, why is the Zweig rule not operative in the pseudoscalar channel? And the answer is probably in GG dual. This was understood by Nathan Isger in early studies.
All right, then let me go on. So
You would have been surprised to hear that supersymmetry would have something to say about this.
No, why? I think there were some works, maybe even Chabot Sackett was present. I don't remember, but what I remember people doing, take super young Mills theory and give a mass just by head. Because in pure super young Mills, of course, Green is massless, you cannot have theta absorbable, but people give small mass just by head. Then theta becomes absorbable and then in full agreement with the general principle, the result is proportional to this small mass. But you can give some estimates, but I don't know, probably that's what he is doing here, but maybe we should
yeah. Yeah, I completely agree with that. Yeah. Okay, so what I'm actually going to talk about is, first, I will just review the standard law in ordinary QCD about eta prime, and given, of course, the Lagrangian and the eta prime potential and the insights we can get from large N QCD. And then in the second part, I'll turn to supersymmetric QCD with anomaly-mediated SUSY breaking. First, I'll give a very short review about SUSY QCD and AMSB, and then I'll show you how to actually construct a chiral Lagrangian supersymmetric QCD from the top down. So you can actually construct the whole chiral Lagrangian from the top down. And then in the very end, if I have time, I'll also comment a little bit on spontaneous CP breaking at theta equals pi. All right. Then let me dive into the first part, eta prime is standard law. Okay, the starting point is, of course, the chiral Lagrangian. What I will consider here is just F flavor QCD with n colors. And as you all know, at the classical level and low energies, the QCD has a flavor symmetry of UF left, UF right, which gets spontaneously broken to its diagonal combination UFD. Which means that in principle, you have at a classical level n squared Goldstone, which you can parameterize in a unitary matrix U, and the Goldstone, which corresponds to the spontaneously broken U1A, would be the eta prime, and the pions are the Goldstone of the spontaneously broken USUF. But since it's a UF symmetry and not U1 times SUF, there's also a ZF factor, which means that the physical range of eta prime is actually constrained. It's not 2 pi, it's not a full U1 Goldstone, but the physical range between 0 and 2 pi over F. Now, this is at the classical level. Yeah, and also want to mention that I always absorb the decay constants within the fields to make them dimensionless. Now, as we know in QCD, there are also quark masses which explicitly break the UF axial symmetry. So you only get a potential for both eta prime and also the pions from that. But we also know that the U1 axial is not actually a symmetry because there's the gauge anomaly. So additionally, this U1 axial is explicitly broken by the anomaly, and therefore you expect the eta prime to be not really a Goldstone, but to be an excitation with the mass of the order of the QCD scale. Now, then you can start writing down the Lagrangian in terms of this Goldstone boson matrix. So this is just the Lagrangian two derivatives, so the leading Lagrangian with the kinetic term and the mass term, which you can find just by Spurian analysis. Then you, of course, also like to introduce the effect of the anomaly into the chiral Lagrangian. And the best way to do that is, again, through Spurian analysis. So the eta prime is the would-be Goldstone boson of U1 axial, so chiral rotations would just shift eta prime. So if the transformation parameter is phi, it would just shift eta prime to eta prime plus 2 phi. At the same time, because of the anomaly, you also get a contribution to Chi dual from the transformation. So instead of theta, you would have theta minus 2 times the number of flavors times phi. So you can, in order to do the Spurian analysis, you assign a transformation behavior to theta, 1 second, and you demand it to transform to theta plus 2f phi under chiral transformations in order to absorb this term that you get from the anomaly. In this way, the Lagrangian would stay invariant, and then you can find an invariant combination of the theta parameter and eta prime, which can be also written in terms of the log that times the U field. This invariant combination can be used in the chiral Lagrangian to construct interactions or terms, including the eta prime. So the question here?
Yes.
Yeah.
Are you on the large limit?
No, this is so far no large n. Large n comes later.
Really?
Yeah.
Because this, I think, only makes sense at large n. Because only in the large n limit is the eta prime actually light. So that it makes sense to keep it in the chiral Lagrangian.
Yes, exactly. Only in large n you can really say it's a PNGD because you recover the axial symmetry in the n to infinity limit. Yeah, I agree. I'll come back to that. This is just, in principle, just from Spurian analysis. In this way, you can more or less construct couplings of eta prime.
It's just that you could also write other things. If you don't have the control offered to you by large n, this is not the only thing you write. But it's an uncontrolled approximation of small n.
Okay, yeah. Okay, so yeah, if you have this combination, then in principle you could add any function of that to the chiral Lagrangian, and it would be consistent with all of your symmetries. And what typically many people write down, but also Tuf wrote down in one of his papers, is this kind of interaction term, where you take the exponential of the invariant combination that I showed earlier. And if you write down this term here, which you also see in many reviews, then you have an implicit assumption, and this implicit assumption is that this term would be generated by instantons. Because instanton effects are also always proportional to integer powers of e to the I theta. So if you write down this term, you have an implicit assumption of its origin. But still, even if you make this assumption, it all seems very consistent. What you find if you write down the potential, you find a potential for the eta prime, and you get a mass proportional to the strong coupling scale, so the lambda QCD, which is much larger than the pion mass. So it seems consistent. Then, of course, the eta prime is much heavier than the pion, so you could just integrate out and derive the typical Kerr Lagrange that we are all used to. Because the eta prime would just try to relax the theta angle, and if there are no quark masses, then it would already solve the strong CP problem by itself. It would just be a QCD scale axion. But if there are quark masses, then it reappears through the U field where you plug in its VEF, and it reappears in the pion Lagrangian. You again have a theta dependence. And then you can just do this regular thing that you always do. You write down a potential for the neutral Goldstone bosons. In this case, it would be a function of the quark masses. And also we have F flavors. So there are F-1 Cartan subalgebra generators, and therefore also F-1 neutral Goldstones. What's also pretty nice to see at this Lagrangian here is one thing that also all of you know: if one of the quark masses is 0, then theta is unphysical, and they can just reabsorb it. Here it's pretty easy to see because we have F cosines, but only F-1 pion fields. But if one of the masses is 0, then you have F-1 cosines and F-1 pion fields, so you can just reabsorb theta within the VEFs of the pions. But if all of the masses are not 0, then you need an extra degree of freedom to reabsorb this theta parameter, which is the axial. All right, now we get to the large N limit. So in a large N limit, for fixed tooth coupling, you see that the anomaly scales like the number of flavors or the number of colors, means the anomaly vanishes in the N to infinity limit. And in that sense, like I said, the eta prime is a two-number Goldstone boson. This is because we recover the axial symmetry in the N to infinity limit. So in this limit, the eta prime would become an exact Goldstone, and it would be completely massless. Now, in the term that we wrote down earlier, this determinant U term, you of course do not see this. In this case, it's not sensitive at all to the number of colors, but also does not vanish in the large N limit. Then back to what we had earlier, we would like to know how the mass of theta prime vanishes in the large N limit. And for this, we can go back to what Britton wrote down in the 70s. He said that the vacuum energy is a function of theta over n. And from this, if we so this is in pure QCD, but if we assume that in large N, the addition of, for example, just one flavor is only a small perturbation, then you can easily find the Veneziano-Witten formula. So you can just make a replacement that we made before. So you can replace theta by this invariant combination, theta minus F eta prime. And then the eta prime mass is just proportional to the topological susceptibility. And if you add right factors of F and F pi, and you see that the eta prime mass squared is proportional to 1 over n, 1 over the number of colors. So this, in principle, implies that if you want to fix the term that we had earlier, then you could write down something like this. You could just take the nth root of the e to the minus I theta determinant U term and add a factor of n in front. This would give you both that the eta prime mass scales like 1 over n, and would also give you the right scaling for meson scattering amplitudes in the large N limit. So it would give you eta prime to the 4 is proportional to 1 over n to the 4 as you would expect.
So you want to modify the Lagrangian in this way, right, to get the right large N.
Exactly. If you modify it in this way, then it's consistent with the large N.
But is this the unique modification? Is it unique?
It's not unique because in principle, so this in principle gives a relation between the terms of different orders. So eta squared, eta to the 4, and so on. In principle, each of them could be independent. So this is more or less just one ansatz with what gives you the right scaling. Yeah.
What's wrong with the formula you showed us before with the log depth, the one that,
Which one?
well, the one from Witten's paper from 1979, the one that you
Okay.
What's wrong with just using that?
There's nothing wrong with that. So you can in principle just write down this log that squared, and you will get the leading contribution would just, well, it would be just an eta prime mass if you add by hand in principle, which is the leading contribution in the 1/n limit. And this would just, so the leading term when you do the expansion large n from this would just agree with that one. This here is just an ansatz what would also give you higher order terms to write n scaling. You of course could also write them all independently, yes. Yeah. And to some extent, this is inspired by what you'll find in supersymmetry. That's maybe what I should have mentioned.
Okay, so so I was going to say why you chose this.
Yeah, exactly. Yeah.
Because it's not,
Wasn't this term discussed in Witten's paper and ruled out?
Huh?
Wasn't this term discussed in that 1979 paper? I vaguely remember it, like,
No, did not
before
always.
my time, obviously.
Yeah.
Semi-obviously, but
If
I'm
I-
pretty sure that Witten discussed this proposal and said there's a problem with it, and you should use log depth. Is that? Correct?
As far as I remember, he discussed the first term that I showed you, just the that U term, and he said there's a problem with that one. He never wrote down this term explicitly. He always had the leading term in large. Yeah, he did not write that one down. Yeah, he just always, for him, he always took the strict large n limit and just kept the leading term in large n.
That's actually exactly what I'm going to zoom in on.
Yeah.
Part of the interruption. I mean,
Sure.
the only place where you may think that this is all systematic is large n, at least for non-supersymmetric theories. So it better work at large n. So does this really get all the large n physics right, including the fact that you should get like a nice consignment theory and domain, data domain walls, all that, which Witten's does.
Okay, we did not go that far. I can't answer that right now.
Okay, fair enough.
Yeah. Okay. Okay, just also this term is perfect to show a few properties that you also find in Witten's argument. So for example, what you get from here is something that looks a bit strange. So you get something like e to the I theta over n. So this term, of course, it's not an instant effect, as we've already discussed. It also seems like a 2-pi periodicity is lost, and also it's a non-analytic function in theta. But this already gives you the solution, because when you take the nth root of a complex number, then you of course also have branches of the complex root. You also have these n branches that you have to add on. But this means what you get in the end is a branch potential. So you also have to keep track of this k from the kth branch of the complex root. And then when you cross from one, when you want to scan the values of theta or eta prime, and you want to recover the periodicity, then you jump from one branch to the next one, and this recovers the periodicity. To make it a bit clearer, so this potential here, just for f equals 2 for two flavors, in this case, the eta prime has a physical range between 0 and pi, so it should better be pi periodic. But if you just take one of these solutions, so for example, k equals 0, then you get this red curve and would be 3 pi periodic. But if you take into account that you have 3 branches, which are all shifted by pi, then you recover the pi periodicity, because once you cross from one branch to the other one, then you will always follow the one which has a smaller potential. And this way you recover the pi periodicity in that case. So in principle, the potential is just the lower envelope of all these branches. And if you integrate out the eta prime, then in principle wash out all of these branches, unfortunately. So you don't see them in the normal Carl Lagrangian. But as I said, the branches are definitely an indication that it's not an instant effect, as we've already said many times. Okay, now what does all of this have to do with the axion? So the axion, as you all know, is the Goldstone of another chiral symmetry, which is anomalous under QCD. So if the axion is a Goldstone, it also shifts under the U1 Petri-Finn transformations, and so does theta. So in this case, the right combination of theta, eta prime, and eta prime would also contain the axion. So this combination gives you the right transformation behaviors under all anomalous symmetries. And then when you go back to the Lagrangian and plug this in, then you see that the potential that the axion gets comes from the same origin as theta prime. So in principle, if you know what generates potential for theta prime, you also know what generates the potential for the axion, which is probably not very surprising. Okay, yeah. Again, it's not changed by IR instantons, but in principle, you can still have additional contributions from instantons from the UV. For example, there are a few models where UV instantons are enhanced. This would be in addition to what we're talking about here. Yeah, and if you integrate our theta prime, then you get the typical result that we are always recommend. Just a small aside that we found pretty neat when writing all of this down. What you typically don't see is a formula for the Axion mass for the general number of flavors, because it seems pretty hard. You have to diagonalize an F times F mass matrix. But here is where EFT really work for you, because if you have a scale separation between F pi and Fa, then you can just integrate out all of the pions, and you find that you only have to solve linear equations to find the Axion mass, which can be written very compactly, and you can even write it in terms of the pion mass matrix. And if you specify it to 2 flavors, then you find exactly what is always written in literature. So this is just a complex formula for the pion for the Axion mass in terms of the pion mass flavors. Okay. So the take-home message from this first part. So the large MPCB, this favors an instant origin of the prime potential and also the Axion potential. It generically leads to a branch theta prime potential, and theta prime washes out branch structure. And of course, all of this is not new, this has been known. But now we want to check if this still holds true in a QCD-like theory, which in our case is supersymmetric QCD. Okay, are there any questions about this part before I go on to supersymmetry? Yeah.
Lead to this branch potential is your postulation, you're asserting that, or everybody agree that potential of this? Can I go back to slide?
Yeah.
Yeah. In this form, everybody agree, or is your
Already Vision found that the theta potential is branched, and well, at least in pure QCD. You have this function of theta over n, then it has to be branched. Otherwise, you won't recover the 2 pi periodicity in theta. So this is not needed now. Yeah.
I think the question of whether it's, det to the power 1 over n versus log det, that's the novelty.
Okay.
So that's your conjecture.
That's a conjecture. Yeah, that's
to make sure.
Inspired by supersymmetry.
You see, near the peak, each time which you change the branch, you don't really know fine details. Because at this point, there are no light or heavy particles, right? At this point, when you jump from one branch to another, everything is of the same order of magnitude, and you cannot integrate out. It means that basically, as a whole, the system doesn't allow to integrate out. In one sector, you can integrate out everything except, let's say, pions.
Yeah. But like physically, what's happening is that those, this, Misha, sorry, but at the places where you have one of these jumps, it's really a theta domain wall, and on theta domain walls, there's some transimus there people figured out over the years, and in that transimus theory, quarks are deconfined on the wall, and so that's like, the central assumption that leads to this is like you have confinement, you have ferrosymmetry, all this is very nice. So like right on the places where you get a branch, you get some interesting physics of the glue. That's basically supporting it.
Yeah.
But on the side, by the way, inside this axion wall, there is a bit of branch for.
Exactly.
But does that mean that it's smooth? It's not as custom?
Well, it's still defined. It's still this low energy approximation is still defined.
But the true potential then would be, if it's the main one, it would be that's, is that kind of idea?
No, if you include all degrees of freedom, if it is, you draw the domain wall just not in the low energy limit. If you could, then of course it will smooth out,
Yeah, that's all I meant.
but we couldn't, right?
Yeah. But it should be smooth.
It's not possible.
Yeah.
No, it's, this peak is erased on the scales of order lambda dynamical scale of the theory. Because you include more heavier, or everything is included there.
Is the smoothing MC dependent?
The thickness of the wall, you have the thickness of the wall.
The resolution of this.
Frankly speaking, I don't remember but maybe in a sense it may be because eta prime mass squared is NC dependent. And it enters in the core, so I expect that if n is very large, eta C prime becomes lighter, and the thickness even of the core grows, and axion are just the huge tails on this scale because their mass is very weak.
Can I have one more question? Can I come back to previous things? I'm getting back to Tony's question about the uniqueness of probably.
Which one? This one?
Like, because your result we heavily rely on this form here. Like this is divided from two things. Like the vacuum's dependence on data over n and for analysis, right? But I don't see any other form other than this which can satisfy both requirements of data over n dependence and invariance on the symmetry that you have to impose in your spread analysis. Like, do you have other form other than this? I think this is only the only form you can have which satisfies that two requirements, which you can rely on to derive this interaction form.
You have to remember one thing: the theta over n, Wittmann only showed this for pure QCD. So once you include flavors, this also changes things. And the second thing is, in principle, in terms of anomalies, you can also write down any function of this theta minus log that U term. Any of these functions would have, in principle, the right anomaly matching structure.
Okay. Okay, I can ask more.
Yeah,
Okay,
of course.
So I think he's gonna motivate this.
Yeah, exactly. Yeah.
Susie, I see.
Yeah.
You have more forms, more blocks.
Yeah. Yeah, this was only meant to be a review and introduction. Okay. All right, then let's start with supersymmetry. So why did we look at supersymmetric QCD? In supersymmetric QCD, you know the amount of adaptive effects because you can really fix the superpotential uniquely. So you know what enters here. And the setup that we have in mind is that we look at supersymmetric QCD with F flavors of quark superfields, and we'll give them a supersymmetric mass MQ, which is much smaller than the strong coupling scale lambda. So what we start out with is a theory with gluons and gluinos, which are exactly massless, and quarks and quarks, which have a mass of the scale of MQ. But then, in order to make it more like QCD, we add supersymmetry breaking, which we parameterize in terms of this parameter M, which is much larger than the quark masses, just like in QCD. The quark masses we imagine them to be small, but it still has to be much smaller than the strong coupling scale in order to retain computational control. Otherwise, you lose computational control. Then what we have is in principle a spectrum that in the IR looks similar to QCD. So you have a massless gluon, like quarks, and then quarks and gluinos, which are at a larger scale proportional to the SUSY breaking.
How many flavors do you have compared to the number of colors?
All of this comes in the next slide. So it's just
okay.
Yeah. So in principle, as I mentioned already earlier, in principle, one would recover ordinary QCD if one could take the limit of SUSY breaking much larger than the strong coupling scale, because then you could really integrate out all the quarks and gluinos. But in this case, calculability breaks down, and it's not even clear if there's a continuous limit to this threshold. And for that reason, it's only QCD-like, because also gaugginos and quarks are, of course, involved in the dynamics. But what is really nice in this setup is that you can construct a Carl Lagrange from the top down. You don't have to rely on spurion analysis, you really construct from the top down. Okay, now is to go a bit deeper into supersymmetric QCD. So we assume it's an SUN, super Young-Mills theory, with F flavors of chiral superfields in the fundamental and anti-fundamental representation of this SUN. And just like QCD, in this case, you have a flavor symmetry of SUF left times SUF right. You have a U1 global symmetry, that's like baryon number, but since it's supersymmetric, you also have a U1R symmetry.
So F is larger than N, right? The number of flavors have to be larger than the number of colors.
No, we are looking at a different scenario. So this, I've not specified that yet. So
Okay.
Okay, so the IR degrees of freedom in this case, for the d-flat directions, can be parameterized in terms of